Let us consider a few questions from CFSE, that is the Crystal Field Stabilization Energy, a few numerical questions. Calculate the CFSE for D4, D5 and D7 tetrahedral complexes. We know these orbitals, degenerate orbitals, split into two sets under the influence of the ligand. So here you have the E set, which are at a lower energy, that is minus 0.6 delta T is the energy associated with it, and this is the barycenter, the dotted line in the middle, and the quantity above it will be positive, that is 0.4 delta T, that much energy higher. So the splitting energy, crystal field splitting energy delta T, this is the gap between the E level and the T2 level. This delta T is small in the case of tetrahedral complexes usually. Then delta T is less than P. P is called the pairing energy. That is, if you have an orbital like this, one electron occupies it. One more electron can come in here. But to put in that electron, energy is needed. And that energy is called the pairing energy. Because when one more electron comes into this, there is repulsion between the electrons. To overcome that repulsion, you need a certain amount of energy, and that is called the pairing energy. But if the pairing energy is greater than delta T, that is this energy gap is less than the pairing energy, then the electron can easily go from a lower level to a higher level. So we do not consider pairing energy usually when we are doing these tetrahedral complexes. When we are calculating CFSE for tetrahedral complexes, we do not add up pairing energy. See, when one more electron comes in here, we say that this orbital, these electrons are spin paired, opposite spins are coming in the same orbital. Now let us look at the formula for calculating CFSE. CFSE is equal to minus 0.6 y plus 0.4 x the whole into delta T, where y is the number of electrons in the E set and x is the number of electrons in the T2 set. E set is the one having lower energy, that is the dx square minus y square dz square orbitals, and the T2 set is the ones having higher energy, that is the dxy, dyz and dxz orbitals. So let us see how to do a D4 complex, that is y number of electrons in the E set. So let us write the configuration. Let us first draw the diagram, that is 1, 2, 3, 4. 4 electrons in that degenerate orbital. Then they are splitting into two sets, the E set and the T2 set. In the E set, there are 1, 2 electrons. And the other 2 electrons will go to the T2 set, 1, 2. So 2 electrons each in the E set and the T2 set. And here also delta T is less than P. That is why these electrons, the other two electrons is going to that T2 level. Otherwise they would have stayed here only. But this energy gap is less than the pairing energy. So they went to the T2 set. So the configuration is like this, E2, T2, 2. Now let us calculate CFSE is equal to minus 0.6 into how many electrons in the E level? E2. So into 2 plus 0.4 into, as per the formula, 0.4 into x. X is the number of electrons in the T2 set. In the T2 set, we have 2 electrons, like here, T2, 2. So into 2, the whole into delta T. That is equal to minus 1.2 plus 0.8. The whole into delta T, which is equal to minus 0.4 delta T. So that is the crystal field stabilization energy of a D4 complex. And this will be a high spin complex because there are unpaired electrons occupying these orbitals. So that is why we call them a high spin complex. Let us look at the second one, that is a D5 complex. Draw the diagram. 1, 2, 3, 4 and 5. 5 electrons occupying these orbitals. They split into 2 sets. That is the T2 set on top and the E set below. So 1, 2, 3, 4, 5 electrons. 2 will come here. 1, 2. Then since this splitting energy is less than the pairing energy, the other 3 will go up. 1, 2, 3. Then here also you have the barycenter, 0.4 into of delta T, that is here, and minus 0.6 delta T here. So calculate, let's write the electronic configuration. That is E. How many electrons in here? 2. E2, and in the T2 set we have 1, 2, 3 electrons. T2, 3. So CFSE equals minus 0.6 into Y, number of electrons in the E set, that is 2, plus 0.4 into number of electrons in the T2 set, 1, 2 and 3, T2, 3, the whole into delta T, that is equal to minus 1.2 plus 1.2, the whole into delta T, which is equal to 0. Minus 1.2 plus 1.2 will give you 0. 0 into delta T, 0. So this is a very stable complex, will be a stable complex as the symmetrical arrangement of the electrons. The electrons are symmetrically arranged. So this will be a very stable complex. Now for D7 complex, let us draw the diagram. 3, 4 and 5. 1, 2, 3, 4, 5, 6, 7 electrons. They split into T2 set and the E set. Delta T less than P, barycenter, 0.4 delta T, minus 0.6 delta T here. So here the configuration is like E, 1, 2, 3, 4, 5. There are 7 electrons in here, 1 electron each in the 5 orbitals now, and then that is out of the 7 electrons, 5 electrons are now occupying E set and the T2 set. Now 2 more electrons are left. So 1 electron will come here and the other will come here. So there are 4 electrons now in the E set. So E4 and T2 are having 1, 2 and 3 electrons. 3. But here you can see that these electrons itself, they themselves are paired. Here also the orbitals are paired. Here also the orbitals are paired like this. Like this. E set. So there is no difference between this and this. So there is no pairing energy involved here also. So let us calculate the CFSE. CFSE is equal to minus 0.6 into how many electrons in the E set? 4 electrons into 4 plus 0.4 into how many electrons in the T2 set? 3 electrons. The whole into delta T. That is equal to minus 2.4 plus 1.2 the whole into delta T, which is equal to minus 1.2 delta T. So that is the CFSE or crystal field stabilization energy for a D7 complex.